So now we know that we can have a time periodic function such as a voltage, where we've got the peak value, we've got the angular frequency, and we've got the independent variable, or we could have some sort of distance periodic function. Our example was a height. We've got some peak height times the cosine of the wave number times the dependent variable, or the independent variable x. So either of these can be what we call phase shift, and by phase shift what we mean is an addition or subtraction to the angular argument. So we would write a phase shifted waveform as Vp cosine of omega t plus or minus some value phi, and so what we want to know is what is this phi, and we could do the same to this argument here. And the purpose of a phase shift is to move a function either to the right or left along the horizontal axis relative to a second function. So here I'm showing two functions that are sinusoidal, a red function here and a blue function, and you can see that there is an angular distance between the two of them. That's going to be measured in radians or degrees, some sort of angular measurement between that point, and that's what we're talking about with the phase shift. So this plot shows a sine wave in red and a cosine wave in blue, and we see that the angular separation between the two here is in theta degrees. So in general, I would write this as so I've got some function, some value as a function of time is equal to its peak value times the cosine of omega t, and we can see that there's if one is sine and one is cosine, we know that there is a pi over 2 phase shift between the two. So said another way, to convert from sine to cosine, we subtract pi over 2 since cosine leads the sine. To convert from cosine to sine, we then would add pi over 2 instead. Sometimes people get confused on the units of a phase shift. Since theta, and often in electromagnetics we actually use phi in this case, but you'll see it both ways. Since phi or theta is the argument, meaning it comes on the inside of this cosine function, its units must be an angular measurement, right? The cosine has to be taken as an angle, so it's got to be radians or degrees. So, this portion here, radians per second times seconds, the seconds are going to cancel. We're going to be left with radians. That's also got to be in units of radians. So, and the same is true in this function. H of x is equal to hp cosine of beta x plus phi. Beta is in radians per meter. It's multiplied by meters. So that still has to be in radians, right? So the argument inside of the cosine function always has to be consistent, and generally we'll use radians. So in both of the cases, the argument of the cosine function is an angular measurement. That's the point I'm trying to make. But the dependent variables are, or the independent variables are time and distance, respectively. So for this reason, sometimes the vertical axis of the sinusoidal plot, the vertical axis, for sometimes the horizontal axis, not the vertical axis, the horizontal axis is going to be presented in both units of angles and in terms of the independent variable. So, for example, here we've plotted time here, but you'll notice that this is in degrees and radians down here. So you would see this as being 0 seconds, and then this is going to be pi over 2 divided by whatever the angular frequency is, and then this is going to be pi over angular frequency. So it sometimes can be a little bit confusing because we'll plot time as a function of seconds along here, but then the units can be radians or degrees, and how you convert between the two is you use this notation right here if we were talking about time, and you use this notation right here if we were talking about distance periodic functions.